Alright, welcome back. In this video, I'm going to be telling you about the 2x2 eigenvalue problem for linear algebra. So to start, I want to talk to you about this matrix multiplication right here. We're going to talk about what happens when I take this matrix, which I will call A, and I multiply it by this vector, which I'm calling X. Okay, AX is going to be a 2x1 vector. Okay, and the first entry is going to be, the inner product of those two things. So it would be 4 plus 2 is 6. And then I will take the dot product of these two things, and I will get 0 plus 6 is also 6. Now, as you can notice that AX is just a scaled up version of X. And that's not what we would expect to happen when we multiply a matrix by a vector, right? Oftentimes these things have aspects of rotation and shifting and stuff like that, and they wouldn't just stay along its own span, is another way of thinking about it. Okay, it's not just going to get scaled up or scaled down. So this is interesting, like what's going on here? So what we're going to be interested in today is situations where AX is equal to some number times X. And we will be using lambda for that number. Okay? We're hoping to solve this equation, really. Figure out the values of lambda that could make this equation true and the vectors x that could make this equation true. So what we're going to do is we're going to set this thing equal to 0, because we know we like solving homogeneous equations. So I'm going to say ax minus lambda x, okay? These are both vectors, so if I subtract two vectors from each other and it's going to equal 0, well, it's going to have to equal the 0 vector. And at this point, I would like to factor the x out of the right side, but I can't do that because A is a matrix and lambda is a number. So I'm going to point out that lambda times x is just the same thing as lambda times the identity matrix times x. What do you think about it? Right? Because the identity matrix times x is just going to be x, and well, if I could scale that up by lambda, and it'd be the exact same thing. So I'm going to say ax minus lambda times the identity x is equal to 0, and then I can factor x on the right. Okay? And we know that with matrices that actually does matter which side we factor on. So that's going to be, what I'm going to be left with is an A minus lambda I. So pretty much what I'm going to be doing is I'm going to be looking for the vectors x that comprise the null space of A minus lambda I. But before I do that, I'm going to have to find the values of lambda that make this possible in the first place. So before I move any farther, I just want to, give lambda a name. Lambda is going to be an eigenvalue for A. Okay? Eigen in some other language means own. And it's some sort of like kind of intrinsic value of A that is, well, that we're going to learn how to find. Okay? And we're going to be interested in situations where A minus lambda I is a singular matrix. Because, well, if it's not, then A minus lambda I times x equals 0 would only return you x equals the 0 vector, right, if A minus lambda I was non-singular. And I am strictly working with square matrices right now. And so if I was to find that A minus lambda I was a singular matrix, I could say that if A minus lambda I was singular and it had an interesting null space, that the vectors in that null space would be eigenvectors for the original matrix A. Okay. The way we're going to attack this problem is pretty much going to be the same every time, at least for a 2x2 matrix. So let's just jump in and do an example. So I'm going to work with that same matrix, and I'm going to try to basically show you how I arrived at getting that special matrix, that special vector that just scaled it up by a factor of 3. So we're interested in situations where A minus lambda times the identity matrix multiplied by some vector x is equal to the 0 vector. Okay, so I need to figure out what is A minus lambda I, but I think the first step would be, what is lambda I? Lambda I is going to be, well, lambda up here along the main diagonal and 0 elsewhere. So that A minus lambda I is equal to 2 minus lambda, 1, 0, and 3 minus lambda. And this one, oh, well, I need to do something to figure out how can I make sure that A minus lambda I is a singular matrix. Now, earlier in this class, I proved to you that a 2 by 2 matrix was singular if and only if AD minus BC was equal to 0. And so I'm going to use that fact on basically this matrix right here. I want to make sure that the product of the top left and bottom right entries minus the other product of the off main diagonal is going to be 0. Okay. So what I need to do there is I'm going to say 2 minus lambda multiplied by 3 minus lambda minus 1 times 0 needs to equal 0 because I need A minus lambda I to be singular. So I'm going to say, oh, that's minus 0, so this is really just 2 minus lambda times 3 minus lambda equaling 0. And so that gives me lambda equals 2 and lambda equals 3. And these are going to be my eigenvalues for A. Okay? So that's the first step in this problem, is find the values of lambda that make A minus lambda I singular. And now that we've got our eigenvalues, we're going to need to kind of dive in and compute the null space of A minus lambda I for these two different values of lambda. So for lambda equals 2, I'm going to be super explicit about A minus lambda I is A minus 2I is the original matrix A minus that matrix with 2, 0, 0, 2, and that's going to be equal to 2 minus 2 is 0, 1 minus 0 is 1, 0 minus 0 is also 0, 3 minus 2 is 1. Okay, so I'm going to just put that in there and replace that. And now I'm going to work on finding the null space of A minus lambda I. So if I wanted to find the null space, I would augment with the 0 vector and row reduce. Okay, so that's not going to be too hard to row reduce. I'm going to just have that. And this is telling me that 0x1 plus 1x2 is equal to 0. So that's telling me that x1 can be whatever it wants, and x2 has to equal 0. So my eigenvectors are x equals x1 and 0. I could say that my eigenspace is the span of the vector 1, 0. Okay? It's the whole x-axis. Okay, but let's actually look at that and look and see at some vectors. Like, let's choose one that's got second component 0. So let's choose 5, 0. Let's look at A multiplied by 5, 0. Okay. A multiplied by 5, 0 is going to be 5 of the first column plus 0 of the second column is going to be, well, 5 of 2, 0 is 10 and 0. And it's just another way of looking at matrix multiplication there. And look at that. That's equal to 2 times 5, 0. Okay. So that's not totally surprising, especially because of that 0 being right there. And I'll have more to say about that in a little bit. But I'm going to move on, and but maybe I'll write my eigenvectors. The set of eigenvectors is the set of all x in R2 for which x2 equals 0. That's a set of eigenvectors. For lambda equals 3, I'm going to take A minus 3I is going to equal 2 minus 3 is negative 1. There's going to be zeros everywhere except for the main diagonal, but that means if I'm subtracting zeros, that's not going to change, right? So that's going to be 1. 0 and 3 minus 3 is also 0. Okay. So if I want to find the null space of A minus 3I, I'm going to augment this thing with the 0 vector and row reduce. Oh, look, it's already row reduced. So I'm going to say this is telling me that negative x1 plus x2 needs to equal 0. That means that x1 is equal to x2. Okay. So one example would be, well, that one I showed you at the beginning. Maybe I'll just do 1, 1. I'll think about what happens if I multiply A by 1, 1. So maybe I'll just actually copy the matrix this time. That's going to be 2 plus 1 is 3, and 0 plus 3 is also 3. And look, that I just scaled up my vector by 3, which is what I said was going to happen with the eigenvalue lambda equals 3. So that's what I'm going to say is that my eigenvectors for this scenario are the set of all vectors in R2 for which x1 is equal to x2. In the familiar xy plane, that would be the set of all points along the line y equals x. All right, now I want to talk about another thing that can happen when we're doing this. Okay, suppose we have a matrix B, which is 0, 1, negative 1, 0. And this is a rotation matrix. And what we'll find is that, well, a rotation matrix can't scale anything up and down, right? Because it's moving everything, this is kind of risky, but, that's my level of drawing. If I rotate this thing like that, well, nothing has stayed in the same place, first of all, and nothing has gotten stretched out or came back along its same, line. So this is probably not going to have any eigenvectors, it feels like. But what I'm going to say is, let's investigate this with the same technique that we did before. B minus lambda times the identity is going to be negative lambda, 1, negative 1, and negative lambda. Okay, the thing that I need to be equal to 0 in order for B minus lambda I to be singular is going to be negative lambda times negative lambda minus negative 1 times 1. I need that to be 0, but I could clean this up and say that's lambda squared minus negative 1 plus 1 is equal to 0. Now, one thing that I kind of forgot to mention earlier is that this is what I would call a characteristic polynomial for that matrix B. Okay, and it's going to be the polynomial whose roots give the eigenvalues. So, but I go over here and I know that, well, that's lambda squared equals negative 1, and so lambda is going to equal plus or minus the square root of negative 1, which we call I, and those aren't real numbers. And so what I'm going to tell you is, at least for now, if you pull back complex eigenvalues, there aren't going to be any eigenvectors. But we will have more to say about the complex eigenvalue situation later in the course. Now, the last thing I'm going to tell you today is just kind of a little teaser of where we're going from here. We've got the idea of triangular matrices. And a matrix is upper triangular if basically all of the entries below the main diagonal are zeros. So like for an example, something like 1, 0, 0, 2, 3, 0, 4, 5, 6. That would be upper triangular because everything below the main diagonal, that 1, 3, 6, it's all zeros. Okay? And lower triangular would be the exact opposite, where all the non-zero entries are appearing kind of down low. So that would be like, maybe I'll do a 4 by 4. 1, 2, 3, 4, 0, 1, 2, 3, something like that, where all the entries above the main diagonal are 0. Okay? And where this is headed is that if you've got yourself a lower triangular or an upper triangular matrix, you can just read the eigenvalues off of the main diagonal. So that matrix has eigenvalues 1, 3, and 6. This one has eigenvalues 1, 1, 4, and 8. And we'll see all sorts of interesting things about what that means when we have a repeated eigenvalue or when we have the eigenvalue problem in higher dimensions. But I don't have anything else to tell you about the 2 by 2 eigenvalue problem. This is where we're headed. Thanks for watching.